Let's try to define what a deployment is. Traditionally, a deployment is a process through which we would install new applications into our servers or update those that are already running with new releases. That was more or less what we were doing from the beginning of the history of our industry. And that is, in its essence, what we are doing today. But as we evolved, our requirements were changing as well. Today, saying that all we expect is for our releases to run is an understatement. Today, we want so much more, and we have technology that can help us fulfill those desires. So what does much more mean today? Applications should be fault tolerant. If an instance of the application dies, it should be brought back up. If a node when an application is running dies, the application should be moved to a healthy node. Even if a whole data center goes down, the system should be able to move the applications that were running there into a healthy one. An alternative would be to recreate the failed nodes or even whole data centers with precisely the same apps that were running there before the outage. However, that is too slow, and frankly speaking, we moved away from that concept the moment we adopted schedulers. That does not mean that failed nodes and failed data centers should not recuperate, but rather that we should not wait for infrastructure to get back to normal. Instead, we should run failed applications, no matter the cause, on healthy nodes as long as there is enough available capacity. Fault tolerance might be the most critical requirement of all. If our application is not running, our users cannot see it. That results in dissatisfaction, loss of profit, churn, and quite a few other adverse outcomes. Still, we will not use fault tolerance as a criterion because Kubernetes makes almost everything fault tolerant. As long as it has enough available capacity, our applications will run. Given that it is an essential requirement, it is off the table because we are fulfilling it no matter the deployment strategy we choose. That is not to say that there is no chance for an application not to recuperate from a failure, but instead that Kubernetes provides a reasonable guarantee of fault tolerance. If things do go terribly wrong, we are likely going to have to do some manual actions no matter which deployment strategy we choose. Long story short, fault tolerance is a given with Kubernetes, and there is no need to think about it in terms of deployment strategy. The next in line is high availability, and that is a trickier one. Being fault tolerant means that the system will recuperate from failure, not that there will be no downtime. If our application goes down, a few moments later, it will be up and running again. Still, those few moments can result in downtime. Depending on many factors, few moments can be translated to milliseconds, seconds, minutes, hours, or even days. It is certainly not the same whether our application is unavailable during milliseconds as opposed to hours. Still, for the sake of brevity, we will assume that any downtime is bad and look at things as black and white. Either there is or there isn't downtime. Or, to be more precise, either there is a considerable downtime or there isn't. What changed over time is what considerable means. In the past, having 99% availability was a worthy goal for many. Today, that figure is unacceptable. Today, we are talking about how many nines there are after the decimal. For some, 99.99% uptime is acceptable. For others, that could be 99.999999%. Now, you might say, my business is important, therefore I want 100% uptime. If anyone says that to you, feel free to respond with, you have no idea what you're talking about. 100% uptime is impossible, assuming that by that we mean real uptime, and not my application runs all the time. Making sure that our application is always running is not that hard. Making sure that not a single request is ever lost, or in other words, that our users perceive our applications being always available, is impossible. By the nature of HTTP, some requests will fail. Even if that never happens, as it will, network might go down, storage might fail, or some other thing might happen. Any of those is bound to produce at least one request without a response or with a 400 or 500 range message. All in all, high availability means that our applications are responding to our users most of the time. By most, we mean at least 99.99%. Even that is a very pessimistic number that would result in one failure for each 10,000 requests. What are the common causes of unavailability? We already discussed those that tend to be the first associations, hardware and software failures. However, those are often not the primary causes of unavailability. You might have missed something in your tests, and that might cause a malfunction. More often than not, those are not failures caused by obvious bugs, but rather by those that manifest themselves a while after a new release is deployed. I will not tell you that you should make sure that there are no bugs because that is impossible. Instead, I will tell you that you should focus on detecting those that sneak into your production. It's as important to try to avoid bugs as to minimize their effect to as few users as possible. So our next requirement will be that our deployments should reduce the number of users affected by bugs. We'll call it progressive rollout. Don't worry if you never heard of that term. We'll explain it in more depth later. Progressive rollout, as you will see later, does allow us to abort upgrades or, to be more precise, not to proceed with them. If something goes wrong, that might not be enough. We might need not only to abort the deployment of a new release, but also to roll back to the one we had before. So we'll add rollback as yet another requirement. We will probably find more requirements directly or indirectly related to high availability, or to inverse it, to unavailability. For now, we will leave those aside and move to yet another vital aspect. We should strive to make our applications responsive. And there are many ways to accomplish that. We can design our apps in a certain way, we can avoid congestion and memory leaks, and we can do many other things. However, right now, that's not the focus. We are interested in things that are directly or indirectly related to deployments. With such a limited scope, scalability is the key to responsiveness. If we need more replicas of our application, it should scale up. Similarly, if we do not need as many, we should scale down and free the resources for some other processes if cost savings are not a good enough reason. Finally, we will add one more requirement. It would be nice if our applications do not use more resources than it is necessary. We can say that scalability provides that. It can scale up and down, but we might want to take it a step further and say that our application should not use almost any resources when they are not in use. We can call that nothing when idle, or use a more commonly term serverless. I will use this as yet another opportunity to express my dislike with that term, given that it implies that there are no servers involved. But since it is a commonly used one, we will stick with it. After all, it is still better than calling it function as a service, since that is just as misleading as serverless. However, serverless is not the real goal. What matters is that our solution is cost effective, so that will be our last requirement. We will explore some of the commonly used deployment strategies and see which of those requirements they fulfill. We will explore the subject in more depth through practical examples. But before we do that, please note that we will be using Jenkins-X. I already used it to create applications with different definitions, one for each deployment strategy. I already deployed the first release of each by pushing changes to Git and letting Jenkins-X reconcile the desired into the actual state. In other words, I will not be deploying anything, I will be pushing things to Git and let Jenkins-X do the magic. Instead of discussing the pros and cons first, we will start each strategy with an example. We will observe the results and, based on that, comment on their advantages and disadvantages, as well as the scenarios when they might be a good fit. In that spirit, let's start with serverless deployments first and see what we will get. And for that, we will use Knative. Knative is what I believe the most likely standard for running serverless deployments in Kubernetes. Nevertheless, the properties of serverless deployments we are going to explore apply equally to almost any other framework. So think of this as a demonstration of universal properties. Let's see how many replicas of the application are currently running. The output states that no resources were found in the namespace. The application is gone. It seems like the application is wiped out completely. And that is true in terms that nothing application specific is running. All that is left are a few Knative definitions and the common resources used for all the applications. What happened is that Knative used telemetry collected from all the pods deployed as Knative applications. And then Knative detected that no requests were sent to the application for a while and decided that the time has come to scale it down. It sent a notification to Knative that executed a series of actions which resulted in the application being scaled to 0 replicas. And all that happened because I did not use this application for a while. If you never use serverless deployments, and if you never worked with Knative, you might think that your users would not be able to access it anymore since the application is not running. Or you might think that it will be scaled up once requests start coming in, but you might be scared that you will lose those sent before the new replicas start running. Let us put that to the test by sending 300 concurrent requests for 30 seconds. We will not go into details about Siege. What matters is that it is sending a certain number of concurrent requests over a specific period, and that period being 30 seconds. So now what we need to do is wait, and wait, and wait, and wait some more until 30 seconds passes. And then we're going to output all the pods with certain name and see what we're going to get. And we can see that the application is up and running again. A few moments ago, the application was not running, and now it is. Not only that, but it was scaled to multiple replicas to accommodate the high number of concurrent requests. High availability is easy in Kubernetes, as long as your applications are designed with that in mind. What that means is that our apps should be scalable and should not contain state. If they cannot be scaled, they cannot be highly available. When a replica fails, and please note that I did not say if, but when, no matter how fast Kubernetes will reschedule it somewhere else, there will be downtime, unless other replicas can take over its load. If there are no other replicas, we are bound to have downtime both due to failures, but also whenever we deploy a new release. So scalability, running more than one replica, is the prerequisite for high availability. At least that's what logic might make us think. In the case of serverless deployments with Knative, not having replicas that can respond to user requests is not an issue, at least not from high availability point of view. While in a normal situation, the requests would fail to receive a response, in our case, they were queued in the gateway and forwarded after the application is up and running. So even if the application is scaled to 0 replicas, if nothing is running, we are still highly available. The major downside is in potential delays when receiving first requests and until the first replica of the application is responsive. The problem we might have with serverless deployments, at least when used in Kubernetes, is responsiveness. If we keep the default settings, our application will scale to 0 if there are no incoming requests. As a result, when someone does send a request to our app, it might take longer than usual until the response is received. That could be a couple of milliseconds, a few seconds, or much longer. It all depends on the size of the container image, whether it is already cached on the node where the pod is scheduled, the amount of time the application needs to initialize, and quite a few other criteria. If we do things right, that delay can be short. Still, any delay reduces the responsiveness of our application, no matter how short or long it is. What we need to do is compare the pros and cons. The results will differ from one app to another. Knative solves quite a few problems. Instead of shutting down our applications at predefined hours and hoping that no one is using them while they're unavailable, we can let Knative, together with Glue or Istio, or basically almost any service mesh, monitor requests. It would scale down if a certain period of inactivity passed. On the other hand, it would scale up if a request is sent to it. Such requests would not be lost but queued until the application becomes available again. All in all, I cannot say that Knative might result in non-responsiveness. What I can say is that it might produce slower responses in some cases, between having none and having some replicas. Such periodical slower responsiveness might produce less negative effect than the good it brings. Review environments might be the best example of wasted resources. Every time we create a pull request, a release is deployed into a temporary environment. That, by itself, is not a waste. The benefits of being able to test and review an application before merging it to master outweighs the fact that most of the time we are not using those applications. Nevertheless, we can do better by converting applications in preview environments into Knative deployments. If the response delay by scaling up from 0 replicas is unacceptable in certain situations, we can still configure Knative to have 1 or more replicas as a minimum. In such a case, we would still benefit from Knative capabilities. For example, the metrics it uses to decide when to scale might be easier or better than those provided by horizontal pod autoscaler. Nevertheless, the result of having Knative deployment with a minimum number of replicas above 0 is similar to the one we would have with using horizontal pod autoscaler. Serverless deployments, at least those implemented with Knative, are probably the most cost-effective deployments we can have. Unlike vendor-specific serverless implementations like AWS Lambda, Azure Functions, and Google Cloud Serverless Platform, we are in almost full control. We can define how many requests are served by a single replica. We control the size of our applications, given that anything that can run in a container can be serverless. We control which metrics are used to make decisions and what are the thresholds. Truth be told, that is likely more complicated than using vendor-specific serverless implementations. It is up to us to decide whether additional complications with Knative outweigh the benefits it brings. And I will leave such a decision in your hands. A long time ago, in a galaxy far, far away, most of the applications were deployed with what today we call the recreate strategy. We will discuss it shortly. For now, we will focus on implementing it and observing the outcome. We will make yet another simple change to the code. We will change the output message of the application. That will allow us to easily see how it behaves before and after the new release is deployed. The Git repository will notify JenkinsX that we made a change. In turn, JenkinsX will run a pipeline that will soon deploy a new release of the application. We will start sending requests to our application before the new release is rolled out. If you're unsure why we need to do that, it will become evident in a few moments. So we created an infinite loop inside which we are sending requests to the application running in staging. To avoid burning my laptop, I also added a short delay of 0.5 seconds. Initially, the output consists of an endless list of hello from JenkinsX Golang HTTP example messages. What matters is the last word example. We changed it in a code to say something else. The important part is the last word that says example, which with the new release should say recreate. And we can see a few moments later that example messages turned into 500 responses. Our application is down. If this was a real-world situation, our users would experience an outage. Some of them might even be so disappointed that they would choose not to stick around and see whether we will recuperate and instead switch to a competing product. The message changed again. And now it is an endless loop of hello from Jenkins X, Golang, HTTP, recreate message. Our application recuperated and it is now operational again. It is showing us the output from the new release. If we could erase from our memory the 500 messages, that would be awesome. What happened was neither pretty nor desirable. But the real question is, why would anyone want to use this? The answer to that question is that no one desires such outcomes, but many are having them anyway. And I will explain soon why we want to use recreate strategy, even though it produces downtime. To answer why would anyone want something like that, we will first explore why was the outage created in the first place. When we deployed the second release using the recreate strategy, Kubernetes first shut down all the instances of the old release. Only when they all ceased to work, it deployed the new release in its place. The downtime we experienced existed between the time the old release was shut down and the time the new one became fully operational. The downtime lasted only for a couple of seconds, but that's because our application boots up very fast. Some other apps might be much slower, and the downtime would be much longer. It is not uncommon for the downtime in such cases to take minutes, and sometimes even hours. We can think of recreate strategy as a big bang. There is no transition period, there are no rolling updates, nor there are any modern deployment practices. The old release is shut down and the new one is put in its place. It's simple and straightforward, but it results in inevitable downtime. Still, the initial question stands. Who would ever want to use recreate strategy? The answer is not that much who wants it, but rather who must use it. One of the common reasons lies in the fact that many applications do not scale. If you have only one replica, Kubernetes will recreate it when it fails, but that will also result in downtime. As a matter of fact, failure and upgrades of single replica applications are more or less the same processes. In both cases, the only replica is shut down and the new one is put in its place. There is downtime between those actions. There are many other reasons, like maybe your release is not backwards compatible and you cannot keep two releases running in parallel, and so on and so forth. There are many reasons, and most of them are based on your architecture, or to be more precise, caused by your architecture. That might lead you to conclude that only single replica applications should use recreate strategy. That is not true. There are many other reasons why the Big Bang deployment strategy should be applied. We won't have time to discuss it all. Instead, I will mention only one more example. The only way to avoid downtime when upgrading applications is to run multiple replicas and start replacing them one by one or in batches. It does not matter how many replicas we shut down and replace with those of the new release. We should be able to avoid downtime as long as there is at least one replica running. So we are likely going to run new releases in parallel with the old ones, at least for a while. We will go through that scenario soon. For now, trust me when I say that running multiple releases of an application in parallel is unavoidable if we are to perform deployments without downtime. That means that our releases must be backwards compatible, that our applications need to version APIs, and that clients need to take that versioning into account when working with our apps. Backwards compatibility is usually the main stumbling block that prevents teams from applying zero downtime deployments. It extends everywhere. Database schemas, APIs, clients, and many other components need to be backwards compatible. All in all, inability to scale, statefulness, a lack of backwards compatibility, and quite a few other things might prevent us from running two releases in parallel. As a result, we are forced to use recreate strategy or something similar. So the real question is not whether anyone wants to use the recreate strategy, but rather who is forced to apply due to the problems usually related to the architecture of an application. If you have a stateful application, the chances are that you have to use that strategy. Similarly, if your application cannot scale, you're probably forced to use it as well. Given that deployment with the recreate strategy inevitably produces downtime, Most teams tend to have less frequent releases. The impact of, let's say, 1 minute of downtime is not that big if you produce it only a couple of times a year. But if we would increase the release frequency, that negative impact would increase as well. Having downtime a couple of times a year is much better than once a month, which is still better than if we would have it once a day. High velocity iterations are out of the question. We cannot deploy releases if we experience downtime each time we do that. In other words, zero downtime deployments are a prerequisite for high-frequency releases to production. Given that the recreate strategy does produce downtime, it stands to reason that it fosters less frequent releases to production as a way to reduce the impact of downtime. We explored one of the only two strategies we can use with Kubernetes deployment resource. As we saw, the non-default recreate is meant to serve legacy applications that are typically stateful and often do not scale. Next, we will see what the Kubernetes community thinks is the default way we should deploy our software. I will change the application's return message so that we can track the change easily from one release to another. Now that I made the changes and push them to the Git repository, Jenkins will make sure that the new release is deployed. Now all that is left is to execute another loop. We will keep sending requests to the application and display the output. After a while, when the new release is deployed, it will suddenly switch to rolling update message. And we need to wait for a few moments for that to happen. And there we go. As you can see, this time there was no downtime. The application switched from one release to another, or so it seems. With the rolling update strategy, the system was gradually increasing replicas of one replica set and decreasing the other. As a result, instead of having big bang deployment, the system was gradually replacing the old release with the new one replica at a time. That means that there was not a single moment without one or the other release available. And during a brief period, both were running in parallel. You saw from the output of the loop that the messages switched from the old to the new release. In real-world scenario, you're likely going to have mixed outputs from both releases. For that reason, it is paramount that releases are backwards compatible. There are quite a few things that could go wrong with rolling updates, but most of them can be resolved by answering positively to two crucial questions. Is your application scalable? Are our new releases backwards compatible? Without scaling, without multiple replicas, rolling update is impossible. And without backwards compatibility, we can expect errors caused by serving requests from multiple versions of our software. We will create a trivial change in the demo application by replacing example in main Go to Canary. Then we will commit and merge it to the master and get a new version in the staging environment. And that will be done in this case by Jenkins X processing that change in a Git repository and rolling out new release. As with the other deployment types, we are about to initiate a loop that continuously sends requests to the application. That will allow us to see whether there is deployment-caused downtime. It will also provide us with the first insight into how Canary deployments work. Until the pipeline starts the deployment, all we are seeing is the old message coming from the previous release. But once the first iteration of the rollout is finished, we should see both the message from the old release and the message from the new release that ends with Canary. And there we go. Since I specified that step weight is 20%, approximately 20% of the requests are now going to the new release, while the rest continues receiving the requests from the old. And after some period of time, whatever is specified in the interval argument of Canary releases, it will increase to 40%. What I forgot to say is that we are using Flagger for Canary deployments. Nevertheless, the logic is the same no matter the tool, even though I think that Flagger is awesome and you should definitely use it, and you should know that this is what I'm using in these examples. You might want to explore other options as well. Based on what we can deduce so far, Canary deployments are behaving in a very similar way as rolling update. The significant difference is that our rolling update examples did not specify any delay, so the process looked almost as if it was instant. If we did specify a delay in rolling updates, and if we had 5 replicas, the output would be nearly the same. But, as you might have guessed, we would not go into trouble of setting up Canary deployments if their behavior is the same as with the rolling update strategy. There is much more going on. But Canary deployments generally shine and make a huge difference is in the progressive rollout. While, as I already mentioned, rolling updates give us that feature as well, the additional control of the process makes Canary deployments true progressive rollout. On top of that, Canary deployments are the only ones that have a built-in mechanism to roll back. While we could extend our pipelines to run tests during and after the deployment and roll back if they fail, the synergy provided by Canary deployments is generally stunning. The process itself decides whether to roll forward, to temporarily halt the process, or to roll back. Such tight integration provides benefits which would require considerable effort to implement with the other deployment strategies. I cannot say that only Canary deployments allow us to roll back automatically, but it is the only deployment strategy that we explored that has rollbacks integrated into the process. And that should come as no surprise, given that Canary deployments rely on using a defined set of rules to decide when to progress with rollouts. It would be strange if the opposite is true. If a machine can decide when to move forward, it can just as well decide when to move back. So which deployment strategy should we choose? Use the recreate strategy when working with legacy applications that often do not scale, that are stateful without replication and are lacking other features that make them not be cloud native. Use rolling update strategy with cloud native applications which, for one reason or another, cannot use Canary deployments. Use the Canary strategy instead of rolling update when you need additional control when to roll forward and when to roll back. Use serverless deployments in permanent environments when you need excellent scaling capabilities or when an application is not in constant use. Finally, use serverless strategy for all the deployments to preview environments, those generated from pull requests, no matter which strategy you're using in staging on production.